Assalamu alaikum. My name is Asad Ali Arshad and my group member's name is Sayyida Muniba Shah. The name of my project is Flexible AC Transmission by Thyristor Switched Static War Compensator being supervised by Dr. Umar Amir Khan. Flexible AC transmission AC here means the power generated at the power plant and then used at the domestic end. This domestic end encompasses everything all around the world, everything around all of us. From the little watch on my wrist to this laptop you are viewing this on, the fans spinning on our heads and the bulbs lighting up our lives. This list does not end here. It also includes all the great big industries which produced daily life products for us. In simple words, modern world is an era of power, electrical power. Now when delivering this power to the consumers, it has to go through long distances and several stages where some of it is lost along the way. But the consumer end requires all of it. This is where this project comes into play. This project ensures the durable and reliable supply of electric power to consumer and compensating for all the mentioned losses. It uses a static var compensator, which is a device designed specifically to measure the power factor of a power system while operation. It judges the condition of the system through this power factor and then uses thyristors to switch components necessary for compensation of the losses. Now, a question may arise that why we are using Thyristor. So now, the answer is simple. Thyristor is a power electronic device and it has no mechanical part, so it switches very fast and smoothly as compared to relay. And further, Thyristor is a 3-terminal unidirectional device, so the thyristors are used in back-to-back configuration in order to conduct for both cycles of AC. Thyristor is controlled through its gate. When the pulse is given at the gate, only then the thyristor allows the current to flow through it. In part 1, a circuit was designed to understand the working and behavior of thyristor. As thyristor is 3 terminals, anode, cathode and gate. In forward conduction mode, when the gate is triggered, then the power flows through anode to cathode. To control the pulse that triggers the gate, a drive circuit is made. So in this figure, as you can see, this is the drive circuit that we made. So in this, it mainly consists of an optocoupler and as thyristors are high voltage components and in complete circuit Arduino would be there to provide the pulse to the gate, so that was a low voltage circuit. So in order to isolate these both circuitries, optocouplers are used. So for testing this, for final testing, a capacitor was added to the circuit in order to improve the power factor. So this is in this circuit we can clearly see that there are back-to-back thyristors applied, and those terminals, these terminals right here, these terminals right here, they are connected to the drive circuit, and these terminals here, the capacitors will be connected in order to improve the power factor. So for this we used a motor, 1 horsepower motor, and we used a power meter to check its power factor. So what we did was, firstly we checked this power factor, that was 0.34, and by using this circuitry, by using back-to-back thyristors, we successfully added the capacitor and the power factor was improved to 0.70. This is the complete circuit. This is the complete software simulation of our project. Firstly, in this circuit, PT is connected in parallel to the source, as we can see, and while CT is connected in series to the source. Further, the two comparators that are connected with CT and PT, the purpose of these comparators is to convert the sine wave into square wave, as XOR only reads high and low logic. So the output of XOR is then fed into Arduino. So the pulse that XOR feeds into the Arduino is used in the formula that is being coded into the Arduino to calculate the power factor. And we have used 3 types of loads: inductive, capacitive and resistive. So now capacitors and inductor branch are present in order to compensate the power factor in any case of the load. So now let's just start with the inductive branch. Let's test inductive branch. So what we will do is, so now let's just start and test firstly the inductive branch, inductive load. So as you can see, the power factor is 0.26 and phase shift is 75 because of the inductive load. So now after a delay of 2 to 3 seconds, these two capacitors will be injected into improving this power factor. Here you can see it's improving the power factor. It's blue right now, it will get red. Yes. So now here we can see the power factor has been improved to 0.97 because these two capacitors have been injected into the system. So now we will begin and test the capacitive load. This capacitive effect here is basically showing the front effect that we see in long transmission lines, where capacitive effect gets added and the voltage lags very much. Here we can see the power factor is minus. This minus is showing that the load is capacitive. So now in order to compensate this inductive branch, this inductor will get added into this and absorb that excess Q and take this power factor to 0.9 or so. Here we can see the power factor has been improved to 0.93 because this inductive branch has been added because of the capacitor in order to cancel this capacitive effect. So now for the final load we have a resistive load. So let's just run, and since we know in resistive load the voltage and current, they are in phase, so the power factor load should be above 0.95, and about here we can see it's 0.99. So this shows that this resistive branch is added right now and the power factor is 0.99. Thank you very much.